Hey, okay, students. As I promised, I would give you a solution guide here, and you could go through and self correct your work and see how you did, and that'll give you some kind of idea. And I will power grade this as quickly as I can, and then you can see your score, and then let you know, and that'll let you know where your grade stands, and then you can make a decision about finals week here. Well, that being said, let me jump into the multiple choice questions. There's 10 of them. Let me start with this first one. It says, as blood flows through the artery. And so I'll draw kind of a pipe here with an artery into a narrow region due to plaque buildup. And so maybe the artery looks like this, but then there's been some plaque that has built up on one side or maybe both sides around it. Anyways, in the artery. And so there's a narrowing of the pipe. And that means the blood has to flow faster in this area. And as we learned from Bernoulli's principle, this faster moving blood would be at a lower pressure. And so that means this over here would be the slower moving blood and the high blood pressure. That's why when the doctor or nurse or PT goes to take your, PA, probably not a PT, goes to take your blood pressure, and they strap it around your upper arm, it's usually somewhere in here, not near where the plaque is built up and not in the main artery. So they end up recording a high blood pressure, and that's a concern for many reasons, but high blood pressure then would show up. So this is going to be the high pressure, this is going to be the low pressure. But it says the blood pressure in the plaque area, so in here, is lower than the pressure in the normal, healthier part. Yeah, so less than or lower. Okay, so there's number one, if you will. All right, so number two says this. Oxygen-rich blood flows at a rate of 20 centimeters per second from an artery with a 5 millimeter diameter into blank number of small capillaries. Okay, so we've got 1 capillary, 200,000 capillaries, 50 million capillaries, 10 billion capillaries. Okay, the blood flow in the capillaries is only, so they slows way down, and the diameter of each capillary is only of this size. Hint, think of all the capillaries as one tube with a cross-sectional area equal to the cross-sectional area of one capillary times the total number. So in other words, kind of like this last picture we had, we've got an artery, but in this case, it's going to be the equivalent of flowing into a bigger pipe, because that big pipe is really made out of a lot of little tiny capillaries. The question is really, one is just ridiculous, but is it, which of these many is it? Okay, so this is the flow rate. I guess it's section 1 that we said the area, the cross-sectional area of this artery times the velocity would equal then to the cross-sectional area of this bigger tube times its velocity. Although, let me write it this way. Let me write it as n times the area of just one capillary. And so I guess I'd have something like this. The area, and they give me the diameter, and they give it me in millimeters. Just to make my life a little bit easier, I'll just do both areas in millimeters, and they'll cancel off here. So this area would be pi times its radius squared. And if it'll be okay with you, I will put diameter squared over, and diameter divided by 2 is the radius. So when I square it, it'll be diameter squared over 4, and its velocity is 20. So that's this side of the equation. N is what I'm trying to solve for, and then this area would be pi times its diameter squared over 4. Diameter, what is this? A blood flow rate of, and in millimeters again, 0.01 squared. Okay. And then the rate, and I just want to be careful here that I do the rate on both sides the same. Let's see, this is in centimeters per second, and then this is also centimeters. So good, there's no tricky units on this one, and that's probably good because this is a hard problem. In fact, I'm going to guess that it's probably the hardest of the multiple choice. That's kind of what it's looking like to me. And then if the units were tricky, that would just make it that much harder. So I'm glad there's nothing tricky about the units here. In fact, the math was made a little easier because there's a pi on each side and there's a 4 on each side. And so now I can get out my calculator and calculate how many this is. So this would be 5 squared times 20 over here on the left-hand side of the equation. And then I will bring this stuff over. So I will divide by 0.01 squared. And whatever that comes out to be, I'll divide by another 0.1. And we're looking at 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 1, 2, 3, and another 1. There. So it looks like 50 million. So must be C there. Wow. Okay. A lot of capillaries. But I do remember in your book, and that's probably why this answer is here, 10 billion. They said that's how many is in the whole human body. So this, these numbers sound a little bit like the brain, if you will. Not really sure how many are in the brain, but that seems like a reasonable amount. Actually, probably even more than that if there's going to be 10 billion in the whole body. Maybe not. But that sounded like that carotid, main one in the neck, what is called the carotid artery. So I think that's what this one is kind of after. Anyways, that'd be the answer. So let's move on here. Here's a dermatologist. They're going to use some liquid nitrogen to freeze, sometimes we say burn off some cancer cells here. That liquid's really cold, 77 Kelvin, and then what it is on the Fahrenheit scale. So maybe the first thing I'll do is get it into Celsius. And so we learned that if you take the Kelvin, 77, and subtract 273, you'll get it on the Celsius scale, which is probably why answer C is here. It kind of throw you for a loop. But we know it's going to change. Oh, change. No, well, yeah, actually, and then I bet it's got to come out to be that one. And then the Fahrenheit was this. The Fahrenheit scale was to take the temperature on the Celsius, multiply by 9/5, and add 32. So I'll take the Celsius and then multiply it by 9/5 and add 32. And we're looking at about a negative 321. Yep, there it is. So that must be D there for the third one. All right, on to number 4 here. A gas in a fixed volume container. So remember we said like P1 V1 over T1's got to be the same as P2 V2 over T2. Actually, we even said number of molecules. But it's a fixed container in terms of volume, so V1 and V2 are the same. They can cancel off on each side. And it says a fixed gas or a gas, or I think we're talking about the same number of molecules here. And so this is what happens when you change temperature and pressure. And sure enough, it's contained at a pressure of 1.5 atmospheres here of pressure and a temperature of 22. Now, probably the only real tricky part in this is that this ideal gas law has to be done on the Kelvin scale. So don't put in 22 for temperature number 1. It would be 22 plus 273, and that's how I got the 295. Whereas then it is warmed to 100 degrees Celsius. So that would be 373 on the Kelvin. So temperature number 2 is 373. And then it asks for this new pressure, P2. And so mathematically, I can just think about bringing this 373 to the other side and then multiplying it by the 1.5 and then divide it by the 295. And it looks like about 1.90. And so I guess C would be the answer for number 4. Number 5, which of the following is not a method for transporting thermal energy? So remember we talked about conduction, convection, and radiation. So there is conduction, there is convection, there is radiation, but the one that is not is condensation. It'll be just kind of something settling and releasing a lot of energy in the process, so it's not completely foreign word to fitting in with our thermal stuff, but it's not moving it from one place to another. 20 or number 6 looks like we've got some kind of material, bone, and trying to find out maybe what kind of bone it is or what it's made out of. And so we're going to look at its properties, like, you know, is it acidic? Is it its mass density? Other properties are nice. How much does it conduct electricity? Does it have any pH values? Anyways, all of that. This is the specific heat. And so the specific heat is this Q. How much energy do you give it? Divided by its mass and its change in temperature. So you find out how much energy it is for each gram, each degree Celsius. And so I'll go ahead and put in my numbers here because we're going to give it 1,600 calories of energy. Has a mass of 255, so that's how much per gram. And now it warmed up 41.5 degrees, and so divided by that to see how much it warmed up per each degree. And so it looks like A here, 0.151 calories per gram for each degree Celsius. All right, number 7, animals, and as you guys probably know very well, need energy. They need to also be energy efficient, otherwise they don't survive real well. But animals need to be energy efficient. One of the ways of walking is, you know, not using your energy to pull your leg back, but let it swing. And so it swings back like a pendulum. You just kind of lift up your foot and let gravity swing it back. But like a pendulum, as it swings it back, and then using no muscle action, so you don't burn any energy, how quickly it swings back is like a pendulum. And the pendulum, you know, depends upon like its length. And so thinking of this as a pendulum, 2 pi square root of L over G, we see that to lower the period, to increase the walking speed, okay? That is to decrease the period. So to get that foot to swing back and forth and to get to swing a little bit faster, we want to make it a little bit lower in length, a lower period. Anyway, so we would be changing the length. And specifically, we would be decreasing its length. And I guess we would accommodate that by kind of lifting up on the foot and how high we lift it. That's why running, you really lift it high and drag the foot right under the buttocks and across. If we're talking about human here. Anyways, although I guess if we're running, we're probably not too interested in energy efficiency. We're burning a lot of energy. 8 here, it says musical notes of F and F sharp are played at the same time on a piano keyboard. The beat frequency, is that difference. And so let's see if we subtract those. It looks like they're 21 apart. And so 8 would be B, just 21. Number 9, which of the following determines the pitch? And so when we talked about sound waves, we said that the human ear is quite fascinating. It can pick up the rate at which the molecules go back and forth. That's the frequency, that's the pitch, and that's what this question is after. So the answer would be B. But it can also pick up how much they move, its amplitude, and that would be its loudness. And so if it was asking about loudness, it would be amplitude. Can't really pick up its speed. And then the last of the multiple choice here, before we get to the harder free response ones, is an emergency vehicle's siren has a frequency of 1200. But an observer will hear a higher frequency. And so this is that Doppler effect. And so it didn't matter if the source or the observer were moving. Could even be both. But if they're coming together, it goes higher. If they're going apart, it went lower. We had a slightly different formula whether the source or the observer was moving. So we do have to pay attention to which one is moving when we do a mathematical calculation. But that's not what this problem is. This is more of a conceptual one. And so as long as they're coming together. And so this first one says the emergency vehicle is moving towards a stationary observer. That would definitely do it. And these other ones wouldn't do it. Moving away, both vehicle and observer are stationary. That would do no Doppler effect, no switch, no change. You would hear just the 1200 moving away. Yeah, so the two moving aways and not moving at all wouldn't do it. It's this one coming together. All right, so again, there's the multiple choice. Let's move on then to the mathematical ones. Let's call this 11A. And it looks like we've got some kind of Bernoulli effect here. The wind comes in and narrows to a tube. And of course, this fits a lot like that. I think that was that very first multiple choice ones. Yeah, both of these. But in particular, this one, where we were talking about the narrowing and it being at a higher speed and a lower pressure. And that's what's going on here. And we can use that lower pressure right here to lift up some mercury and then measure that pressure in millimeters of mercury, which is a common unit in the biological world here. Okay. And so let me just point out that there is 133 pascals in 1 millimeter of mercury. Okay. That was our common conversion in class. I almost want to change this to centimeters because I think they go on to say, that the height is 5.4 centimeters. So why don't I multiply this by 10? So 1 centimeter of mercury is equal to 1,330 pascals. So either unit conversion is fine. But it is the fact that it narrows is going to say something about the speed. And that's this problem. It says a research biologist is studying the effect that wind has on insects. So one of the things the biologist would want to measure is the wind speed. So the researcher uses this crazy thing called a Venturi meter. And so this Venturi meter to measure the wind speed. The Venturi meter looks like this. And so the wind comes in, looks like it narrows, spreads out. This narrowing would be a lower pressure. That would lift up the mercury by a height higher than that. So this would be the pressure difference between 2 and 1. And that's what you want to get out of studying this. The wind enters at the left at a speed of v, right there. The diameter, and they give you the diameter of the pipe. Okay, good. At 0.1 in the diagram, narrows to 1 centimeter at 0.2. The U-shape manometer is filled with mercury. When H equals 5.4 centimeters, what is the wind speed? And this is a tough problem. I think this is the hardest one on the exam. And so there's fortunately some hints given here. It says this is a Bernoulli effect problem. Go ahead and look at section 12.2. And it also has some flow rate in it from the section before that, 12.1. And so let me start with Bernoulli's equation. Bernoulli's equation says if you have point number 1 and take its kinetic energy, its gravitational potential energy, and its pressure energy, that would be the energy some chunk of air has right here. And as it flows through and narrows, the energy has to be conserved. However, it may change into a different amount of kinetic or a different amount of potential energy or a different amount of pressure energy. And we can hopefully see here in the diagram that the height doesn't really change. I mean, the biologist, if you had a big picture, would be standing and the ground would be way down here. This is not, this is a horizontal wind. Anyways, kind of like our homework, this is about wind speed. It's not about a difference in height. So I'll add it to the original equation only to cross it out. And so whatever the height is, maybe the researcher's holding it like a meter and a half above the ground. They're going to be the same on both sides. So I'll cancel that off. And in fact, we talked about this back on problem 1, but in this narrowing spot, it's got to go faster to get that same amount of air through. Therefore, the pressure is lower. So pressure at 2 is lower than 1. So I'm going to write this as this, P1 minus P2. By bringing the P2 to the other side. And I'm going to say that this right here then is going to be greater than 0 because pressure number 2 is going to drop. And basically it's because this speed picks up. And so in terms of energy, what we're saying here is we're going to lose pressure energy. And where does it show up? Well, more kinetic energy. So the total energy doesn't change. And then, of course, I can write this as 1/2 rho, and then I'll have a V2 squared minus a 1/2 rho V1 squared. And so if I can get these two different speeds plus the density of air, we're golden. Now, the density of air is given in the book. It varies a little bit with temperature. I'm going to go ahead and use kind of the standard 1.22 kilograms per cubic meter. I'm not going to really be nitpicky on which one you use, and so somewhere in that ballpark is fine. What I'm trying to find in this particular problem, though, is V1, the speed right here. And of course, that means I, have this challenge that I need to not only know the density, but to get V1, I also need to know V2, which, as we said, was faster than V1. And we also need to know the pressure difference, the P1 minus the P2. Now, fortunately, this one's pretty easy. That's why I thought I would do it. This is the whole reason why the mercury is higher, because of this low pressure, and it's higher because of this. And since it's made out of mercury, it would be, you know, for every 1 centimeter the mercury rises, it's 1,330 pascals. And so I have 5.4 times that. So I'm going to put this as 1,330 pascals for every centimeter of mercury, and then say that I have 5.4 centimeters of mercury. And then this would convert the units that is used a lot in biology and into ones that have to do with energy, because a Pascal is the Newton and the joules. So let's see, this would be 1,330 times 5.4. So this would be 7,182 pascals. All right, so back up to here. So, okay, so I got this pressure difference, and I got the densities, okay. The other hard part of this problem, so like I said, it's a pretty hard problem, is to do this flow rate, if you will. And that is the cross-sectional area times V1 would equal cross-sectional area times V2. This sounds a lot like the other hard one we did back in the multiple choice. There was a second one on here. So this flow rate one. And so in my case, I'm going to kind of do what I did before. The area, again, of this first tube would be pi r squared. Now, if you'll let me write it as a diameter, 2.54 squared over 4. Because again, diameter divided by 2 is the radius, and when you square it, you're going to get diameter squared over 4. So that would be the area in square centimeters. And so I better be careful to make sure my area on the other side is also square centimeters. And it would look like this, pi times 1.0 squared over 4. Because again, what did they say? The narrows to a diameter of 1 centimeter. So fortunately, because there's a lot of other hard things in here, this is a lot like number 2, where the units were good to us. Or you can convert the unit, but that's, I guess, an unnecessary step. So those numbers I know. Here's the thing, though. I don't know either of these two velocities. But this can give me the velocity of 1 or 2 in relationship to each other, which I can now use back up here. And that's perfect, because now I have what we would say 2 unknowns in this one, V1 and V2, and 2 unknowns in this one, V1 and 2. And so I have a system of equations, 2 equations with 2 unknowns. So maybe the way to go about this one is to write this one in terms of V2, so that when I put it into my original one back here, I get rid of the V2s and I only have an equation with V1 in it, which is what I'm trying to solve for. What is V1? So that's kind of my thinking here. And again, like we saw for number 2, is it's really kind of nice when we, write things in terms of the diameter squared, because the 4's cancel on both sides and the pi's cancel on both sides. And again, We saw that on this hard one here on number 2. Okay. These numbers were kind of nice because a 1 squared is just a 1. So it looks like all I really have is 2.54 squared times V1 is V2. So after all that thinking about units and looking like it was going to get hard, it actually fell into something easy. So again, this is our flow rate. This is our section 12.1. That's the hint to look at that, because I'm going to use that back in where we got started, which was section 12.2 for the Bernoulli effect here. Okay. And so let me put this all together. P1 minus P2. That was this thing. That was this 7,185 pascals. And then here I have a 1/2. And if you let me put in my rho of 1.22. And now if you let me put in my V2, this was this whole point, and it's V2 squared, that would make 2.54. And it's already squared, so if I square it again, because I got to put velocity squared, that's to a 4th power, and then V1 squared, minus 1/2 times this rho, 1.22-ish, times V1 squared. All right. So again, there's that tough math. I got 2. In fact, maybe I should keep circling them there. This is the first equation from section 12.2, Bernoulli. And this is the second equation from the continuity. So we've got 2 equations, 2 unknowns. Our 2 unknowns are V1 and V2, and everything else is given either directly or somewhat indirectly, like area in terms of the diameter. Okay. And so once I solve this for V2 and put it into here, I should have an equation now that only has a V1, and that's what I'm after, solving for that V1. What is the wind speed? Now maybe I'll just do this in a couple of steps. 7,185 here. Just grabbing my calculator. I'll take the 1/2 times 1.22 times... Ooh. I'm kind of concerned about my units here, but they would cancel off. So this just is a number. Okay, good. 2.45 raised to a power of 4. So this would be 25.39 V1 squared. And this would be 0.5 times 1.22, 0.61 V1 squared. And so if you let me come up here, copy that and subtract, copy that one. We're looking here at about a 24.78 V1 squared. And then taking this 7,185 and dividing it by that last answer, this would be 289.95. And then finally, a square root. There are a lot of mathematics. And we're looking at about 17.0 meters per second. All right, wow. That's a good problem. And very much so, I would say, the hardest one. Although maybe I'd be very careful and look at the other 2. But I've looked out at them before, and obviously I selected them and looked at them, and I liked them, and those were good ones, but that's a really a good one here. All right, so let's do the second free response one. So we'll call this 11B. And this falls into our thermal conductivity one. This is actually very much like a problem, so I hope this one went well for you. I could understand between the math and all the details of this 11A might be a little tricky for you. But this one was an exact copy out of the book with just a different material and a different animal and different numbers. But the hint even says, look, if you did chapter 14, number 36, this is a lot like that. And so it says, assume that all the feathers on a goose on a goose are down feathers. And I know that's not quite true, because aren't the down feathers just the kind of the ones on the inside? But other than that being a little unreasonable, and they give us its thickness, they give us the skin temperature, they give us the outside temperature. Let's see what else. They give us the surface area of the bird here, and it says then how many calories, and it's a capital C. So that might be, if anything's kind of tricky, it might be that part of it, because I've got to do kind of this unit conversion and keep track of all of that. But it even says that, you're going to need table 14.3. And in fact, while I'm talking here, why don't I just open up your book here again and go to table 14.3. Because the formula we need, it's actually 14.26, says that the rate of energy exchanged is the thermal conductivity, the area, the temperature difference, and then the thickness of the material. And so as I scroll down here to table 3, kind of near the bottom, they say that the thermal conductivity of down feathers, kind of those inside, very warming feathers, is really small, and that's the whole point. Now, the units here would be joules per second, meter, degrees Celsius. So we're going to get a rate here in joules. The area was given straight up as 0.45 meters squared. The temperatures was given straight up as 32 minus a negative 10. And the thickness, and here's probably where one place we've got to be careful with our units, is given in centimeters. And everything else is the base units of joules, which has a meter in it, and meter. So let's make sure we get that into a meter. So 0.0175 meters. Oh, and I should have put degrees Celsius here. Because you can see now that the square meters in the numerator go with a meter on each side downstairs. And a degree Celsius does. And so we're going to be left with a flow rate in joules per second. And then, so I can go 0.025 times 0.45 times, looks like that's going to be a 42, divided by 0.0175. And so we're looking at about a 27.0 joules per second in thermal energy that is flowing out of the skin through the feathers into the environment. And so the goose here needs to burn some of its energy, some of its food or fat or whatever, in order to keep warm. And so for a whole day, how many calories with capital C would this be? So I guess I would say this is kind of the first step, and really kind of the main step of this problem. But since that's our rate, you can do, something like this. The total energy then is, power, or maybe I should write power is energy over time, or put another way, total energy is power multiplied by time, or rate multiplied by time. So our power, or our rate, being 27.0 joules per second, needs to be multiplied by the number of seconds, another unit thing here for the number of seconds in one day. So we have 24 hours, and then times 60 minutes in an hour, and then 60 seconds in a minute. So hours cancel off, minutes cancels off, and then seconds cancel off, and finally we get joules. Still not quite done, but a good start. And so let's go 27 times 24 times 60 times 60. So we are looking at 233 2800. 123 123. So about 2.3 million joules of thermal energy are going to kind of leak out of the skin of this goose. Now, again, more unit conversion here. So I'll just rewrite that number and give myself a little space. And so to get rid of joules and turn it into calories, I've got to say that there's 4.186 joules in 1 calorie. And this is how we get it into calories with a small c. And then we can get rid of the small calorie and then have the big calorie, because there is 1,000 little calories in 1 big calorie. And that'll get rid of the little calorie and onto the big calorie, the kind of units that nutritionists and probably you guys in biology probably appreciate a little bit more than the physical sciences, where we like the joules. All right, so I'm going to take that energy and I'm going to divide it by the 4.186. Then I will divide that by the 1,000. And we are then looking at 557 big calories needed to stay warm under these conditions. And yay, hope that went for you. Okay, so again, thermal conductivity, just like the problem, and then a bunch of units conversion. All right, well, on to the last problem, 11C. And I think this is the easier of the 3 free response ones. It says that the musical note A4. So let's see, A4. Let's see, middle C would be C4. Huh. I was going to say this is this would be the A above middle C, definitely. Okay, so the A above middle C is 440, but none of that musical stuff matters. It's just we need this frequency. So the frequency is 440. And the first part here, A, says, what is the wavelength of A4 in a concert hall? And I put in parentheses, normal room temperature. So wavelength is velocity times frequency. The frequency is given straight up, so that's pretty obvious one. And then our speed, we could hopefully just have remembered the famous one, 344 meters per second. That's what we get at room temperature. But we can also dig up this equation that says the speed depends on its temperature on the Kelvin scale. divided by 273, and then you take the square root of that, multiply by 331, and you get the speed of our sound. And if you put in room temperature, which is about 22 degrees Celsius, which would be 295 Kelvin, you'll get this number. So I wasn't really expecting you to use this equation yet. That's going to happen in B. But for starters, it was just kind of a straightforward 344 divided by, 344 divided by 440. I was kind of blocking my equation. And then I will get a wavelength of about 0.781 meters. So there's the first part of it. What is the wavelength? But then this concert is taken to an outdoor arena in the desert, so at Burning Man here. What's the wavelength when the temperature is very warm, 36 degrees Celsius? So maybe before I even start the calculation, I should find out what the speed of sound is at that warm environment. So it'd be 273 plus 36 to get it on the Kelvin scale. So that's kind of the big piece there. So 273 plus 36. Okay, so it's 309 on the Kelvin scale. And if you divide that by 273 and take its square root, and then that factor, so it looks like a 6% increase over 331, gives me a speed of about 352 meters per second. And this fits into what we were talking about here for the speed of sound in air. Room temperature, then, room temperature being about 22, should be then lower than this, but yet still higher than 331, and that's this 344. So all those numbers look really good. This is just a little bit faster than it was at room temperature. But now it's really the same calculation. You just take this velocity and divide it by its frequency. So its velocity is 352, and its frequency is 440. And all this 352 divided by 440, and I get a little bit bigger wavelength at 0.08 meters. And that was good and way, way easier than 11A. All right, well, I hope you did well, and what you might have missed, I hope this video has kind of helped you not only pinpoint what you missed, but why you missed it. And hopefully, again, learning from that so you don't make that mistake again. And even though we're coming to the end of this semester, all this material and definitely the thinking process carries on to next semester. And so hopefully that will all help you moving forward. And if you're taking the final exam, hopefully it'll put you in a position where you won't make that mistake a second time. All right. Take care, everyone. Bye now.